You ever stop and think about what makes something groundbreaking? You know? Behind every cool invention or piece of tech we use every day, there's this secret story. And it's not just about a clever design. Nope. It's all about the stuff it's made of. So, yeah, let's dive into that world. All right, let's kick things off with a little puzzle for you. Think about this. A race car's brakes, a super precise surgical robot, and a xylophone. I mean, on the face of it, they couldn't be more different, right? You've got extreme speed and heat. Then you've got this delicate, life-saving precision, and then just beautiful music. So what's the connection? What do they all have in common? Well, the answer is actually pretty simple, but it's also incredibly powerful. Every single one of them is a masterclass in material science. Their success, the very reason they work at all, comes down to an engineer finding or even inventing the perfect material for that specific job. And that right there, that's the core idea we're talking about today. It's this unseen foundation that honestly supports just about everything in our modern world. So what is material science really? A good way to think about it is like the ultimate matchmaking service for engineers. It's all about understanding a material's personality, how it behaves, how you can shape it, and how its deep down internal structure gives it these totally unique powers. And you're doing all that just to solve one specific problem. But here's the thing, picking a material is never simple. It's not like just grabbing something off a shelf. Engineers have this whole checklist they're constantly juggling. I mean, you could find the strongest stuff on the planet, but can you afford it? Can you actually make a million of them? And what about its environmental footprint? Every single one of those questions is a massive trade-off. Okay, so let's see that checklist in action. And what better place to start than transportation? This is a field that is always pushing the absolute limits of what materials are capable of. And the solutions are not always what you'd think. To tick all those boxes on the checklist, especially the environmental one, researchers are getting seriously creative. Get this, they're testing things like hazelnut shell powder for eco-friendly brake pads. Yeah, literally. It's just a perfect example of that outside-the-box thinking. This really gets to the heart of a huge battle in the car and airplane world, the constant fight between strength and weight. For years and years, steel was the undisputed king. It was strong, reliable, but it's heavy. And if you want better fuel efficiency, you have to shed weight. But you can't compromise on safety. That's where these advanced composites come into play. You take a lightweight metal, say aluminum, and you mix in these microscopic particles that act like a super strong skeleton, giving it incredible strength. But here's the thing, even just saying aluminum is way too simple. It's not one thing, it's a whole family. An engineer isn't just grabbing aluminum. They're picking a very specific recipe, an alloy, like AA7075, that's been tweaked and perfected for something like an airplane wing that has to handle tons of stress. And that's a completely different beast from the general-purpose AA6061 you'd find in, say, a bike frame. And this innovation, it goes all the way down to the tiniest, most microscopic level. To squeeze more efficiency out of engines, scientists are basically engineering friction itself. They're creating these nanolubricants using wild materials like graphene and carbon nanotubes, all to cut down on wear and tear and save a little more energy. All right, so we've talked about how materials perform, but what about how we make things with them? Let's jump into the world of manufacturing. We're going to see everything from turning trash into treasure to literally printing parts on demand. Okay, this is such a great story of what we call circular design. You start with something we all throw away, that rigid plastic, HDPE, from milk jugs and shampoo bottles. And through a pretty straightforward process, you collect it, you crush it up, you process it, you can turn that waste into these super strong, durable building panels. It's an amazing, low-cost, high-impact idea. And then, of course, there's 3D printing. It has totally changed the game for how we made stuff. But, and you're probably sensing a theme here, the material is everything. You might pick a tough plastic like ABS for a part that needs to be strong. Or if you want a greener option, you can use PLA, which is often made from things like cornstarch. And for the really intense jobs, you can even print with nylon that's been reinforced with things like aramid fibers, the same stuff in body armor. But, with all this shiny new innovation, we can't forget the classics, the old reliables. Simple, well-understood materials like mild steel. You'll see names like S30C or S45C. They're still the absolute workhorses of industry. They are the literal backbone of so many machines, just because they're cheap, they're predictable, and they just work. Okay, let's shift gears now to probably the most complex and high-stakes environment there is, the human body. When you're engineering for this, the choices you make are quite literally a matter of life and death. The number one absolute golden rule here is something called biocompatibility, which is just a fancy way of saying the body has to accept it. You can't just stick any old material inside a person. The immune system will go on the attack. And this challenge has led to some incredible innovations. For example, beta titanium alloys. They're not just strong, they're designed from the ground up to leave out any elements that could be toxic. Or how about this, taking regular bone cement and beefing it up with carbon fiber so that a hip replacement is stronger and lasts way longer. And to really get it right, you have to do more than just make sure the body doesn't reject it. You have to mimic how the body behaves. See, most materials we use are linear elastic. It's like a spring. You pull it, it stretches in a nice, predictable way. But our own bodies, our skin, our tissues, they're hyperelastic. They stretch in all these weird, complex, non-linear ways. So the holy grail is creating materials that can copy that squishy, unpredictable behavior. That's the secret to making better implants and, get this, the next generation of soft, flexible surgical robots. Okay, so we've seen where things are now. But what's next? Where is all this heading? Let's take a quick peek at the future, at the real cutting edge. The future is all about custom design, right down to the atom. We're talking about scientists designing new metal alloys on a computer, atom by atom, before they even make them. We're talking about advanced resins that make 3D printed parts as strong as machined metal, special plastics that can handle the insane heat inside a jet engine. And bringing it all the way back to the beginning, to our xylophone, we're even talking about creating new composites that can perfectly copy and maybe even improve on the beautiful sound of rare traditional woods. And this quote just nails it. For most of human history, we've had to design things based on the materials we had available. But now, we're flipping that script. We are starting to design the materials themselves to make technologies possible that we could only dream of before. Which kind of leaves us with one last big thought. When you think about the world's biggest challenges, clean energy, fresh water, exploring space, so many of them, when you dig down deep, are actually material science problems. So really, the question isn't if a new wonder material is on its way. The real question is, what global problem is it going to solve?